Hi, and welcome to Module 7 of Lecture 2. In this module, we're going to cover the situation in which we have two continuous variables, a continuous dependent variable and a continuous independent variable, putting us in the lower right corner of this 2x2 table we had from before. Okay, to do this, we're going to calculate something called a correlation coefficient, often represented as R. The goal of this correlation coefficient is to capture the extent to which changes in x are correlated with changes in y, or the degree to which x and y have their changes associated with each other. This relates directly to prediction as well. If we knew exactly, if x and y are perfectly correlated, we could predict y's values or y's changes from x's changes. So, and this is for bivariate correlation. We'll later extend this a little bit when we have more than one independent variable, but for now we're going to stick to bivariate correlation between 1x and 1y. The nice thing about this is, in contrast to the chi-squared, we're not only going to measure association, we're also going to measure the strength of the association and the direction of the association at the same time. So we get more information out of R, which makes some sense because R is dealing with two continuous variables as opposed to two discrete categorical variables. So there's more information available. It's kind of the difference between looking at a mean and standard deviation versus something like a mode, which has much less information about the overall distribution. Okay, so before we do any stuff, we need to understand one concept of the covariation. The extent to which two variables move together is called covariation. And the statistic that measures covariation is very similar to the statistic that measures the variation in a single variable. The primary difference is the covariance here, represented by covariance xy, instead of being the sum of the deviations between x and its sample mean squared divided by n minus 1, it's the sum of the multiplication of the deviations in x and the deviations in y. So the only difference is, instead of having this second parenthetical expression right here where the mouse is moving, instead of having another xi minus x bar, which would make xi minus x bar squared, you replace it with yi minus y bar. So it's the sum of the deviations in x and the corresponding deviations in y. It works very nicely by doing that, because if a particular value of x sub I is greater than its mean, and that corresponding yi is also greater than its mean, then you get a positive value to be added to the sum, to the correlation, to the covariation sum. Or if one xi is less than its mean, and the other yi is also less than its mean, you get two negative values, which when multiplied give you a positive value. So as long as you have increases in x associated with increases in y, or decreases in x associated with decreases in y, you get positive values for the covariance, and you have positive covariance. In contrast, if you have increases in x associated with decreases in y, or decreases in x associated with increases in y, then this formula will give you one positive value times one negative value, which will give you a negative term to add to the sum. If you have uniformly negative terms, you'll have a negative covariance. So, and then when you have some that show positive covariance and some that show negative covariance, they'll add up to something closer to 0, and you won't see a strong correlation covariance between the two variables. So this pretty straightforward equation, once you have seen the variance, is a nice way of capturing the degree to which two variables move together. So let's look at an example here. This, for a hypothesis for this example, we're going to say we're going to hypothesize that states with low per capita incomes, in those states you see government employing more workers. We have a very small sample here of 7 states, all in the South, and here are per capita incomes and percent government employees. The null hypothesis, of course, is implied by this research hypothesis, which is the per capita income of states has no relationship with the percentage of workers employed by state governments. Okay, so step 1, we have our x is the per capita income, that's our independent variable. Our y is our percentage of government employees. That's our dependent variable. Our hypothesis says that as we decrease per capita income, we increase percentage of government employees. Or you could say it as I increase per capita income, I decrease percent government employees. So the first step here is to calculate the mean for each variable, because we can't take deviations until we have the means. So here are the means for the two different variables in the data from the previous slide. Okay. Now that we have those means in the second and fifth columns respectively, we can calculate deviations for all 7 data points, and they're here on this slide. Now once we have those deviations, which are repeated here, we can multiply the deviation in x times deviation in y for each corresponding data point. And that gives us this series of 7 multiplied deviations. Note in this case they're all negative. So the sum is also negative and reasonably large. The covariance is calculated by taking that sum and dividing by n minus 1. The minus 1 is for the same reasons we discussed before for the sample variance, because you lose 1 degree of freedom by fixing the mean, and you get negative 53 approximately. Okay, and this is the sample covariance of the data between x and y. Why is it negative? Well, if you look at each individual data point, every single time in this data set that the per capita income is below the mean, the percent government employees is above the mean, and vice versa. So Alabama here has below the mean per capita income and above government employees, whereas Florida has above the mean for income and below the mean for employees. So every single time you get their x and y are moving in opposite directions, and therefore the product is negative of the deviations, and therefore the covariance is also negative. You can look at this visually, and it's a really good habit to get into to graph your data before you do anything else with it. So here you have per capita income on the y-axis, and percent of government employees in the x-axis. This is kind of backwards. Usually you would put it in the other direction. Either way, you get a negative relationship, but usually you put the dependent variable on the y-axis and the independent on the x. Anyway, either way, you would get a relationship like this, in which you have a downward sloping line kind of connecting all different points. Okay, now, how to calculate the correlation coefficient. It's pretty close to the covariance, but normalized based on the variance of each individual variable. So we use what's called the Pearson's correlation coefficient, or R, lowercase r, and it's equal to the covariance we just calculated divided by the square root of the variance of x times the variance of y. So the reason, again, you divide by these two variances is you're basically normalizing the covariance to take into account how much variation you have in the underlying variables themselves. It could be the covariance seems very big, but that's because the variances are very big, and actually there's not, given how much variation there is anyway in the variables, the covariance is seemingly less important than you might have otherwise thought. So we just calculated the covariance. We need to do the same thing for the variances. So we can do that if you go back to the data. The covariance you just saw, the variance in x is very, very large. The numbers are large. The variance in y is this. You plug into the formula we just saw. Here's the covariance on top. This on the bottom is the square root of the variance in x times the variance in y. Now we get negative 0.936. So again, it's the same sign as the covariance, and it has to be because the bottom of this r is always going to be positive, which is the positive square root. But now it has a, as we'll see in a second, it has a more natural interpretation. Okay, so r itself has a range between 1 and negative 1. If r is 1, positive 1, there's a perfect positive correlation. If r is negative 1, there's a perfect negative correlation. In our case, with over negative 0.9, we have a very, very strong negative correlation. And as you can kind of tell from the plot, this looks extremely consistent and negative. Okay, so the nice thing is we can predict the dependent variable from the independent variable when r is 1, because we know exactly how they're correlated, and they're correlated perfectly. In our case, even though they're not perfectly correlated, they're correlated well enough that we can guess with a decently high degree of accuracy what's going to happen when if I were to decrease the per capita income, for instance. I wouldn't be exactly correct, but I could guess with a decently high degree of accuracy. When R was 1 or R is -1, you can guess with perfect accuracy. Okay. When R is 0, in contrast, there's no relationship. That's the null hypothesis you're going to be testing here, is R equals 0, which means there's no relationship, no association between x and y. And then the nice thing is, it tells you the strength as well, right? As R gets closer to the extreme of 1 or -1, the relationship gets stronger. So a -0.8 is a very strong relationship, whereas a 0.3 is less strong. So it gives you direction in the sign of R, the strength in the magnitude of R. All it's left to talk about is statistical significance to see whether or not this correlation is meaningfully different from 0, statistically different, statistically significant, and allows us to reject the null hypothesis that R actually is 0. Before we get there, though, a couple things to remember. This assumes a linear relationship between the two variables. So it assumes that as x increases by some value, y increases linearly by some multiple of that value. It is not appropriate if you have a theory that says y should be related to x squared or x cubed or some more complicated function of x. And again, as usual, the fact that we have a strong linear relationship, a strong correlation between x and y, does not mean there's any causal relationship between x and y. For all the reasons we went through before, including the one listed here, which is that if we flipped independent and dependent variables, we'd still have the exact same relationship. The exact equation would hold exactly the same to calculate R, and yet now y would be causing x if we had assumed causality was true. So we can't, as usual, tell causality from correlation. Okay. Now, back to the t-test. So what we have so far is a correlation coefficient, which gives us, it's a measure of association, magnitude / strength, and also direction. What we don't have is significance, because we haven't yet dealt with the fact that there's uncertainty around our calculation of the correlation coefficient, because it's calculated from sample parameters, and these parameters have associated uncertainty with them. So we're going to have to figure out a way to test for a statistical significance of a correlation coefficient to see if we can reject the null hypothesis, the thing we calculated was statistically significantly different from 0, which is our null hypothesis here. R equals 0 means there's no association between x and y, which is our null hypothesis. If we can reject that null, we are confident there's an association between the two variables. So how do we do that? We're going to do that via something called the student t-distribution, which is useful for smaller sizes of data. We said before, when n is big enough, you can assume a normal distribution for some of this stuff. In this case, if you had over 100 data points, we could assume a normal distribution and use the critical values we've seen before. In this case, we have 7 data points. That's far from normal distribution. So we're going to use a different distribution called the student's t-distribution, which is very similar to the normal. It has fatter tails, they call them. So a normal is a bell curve. The t-distribution has a flatter center and taller tails. So to do this, we're going to do the same kind of thing we did for the chi-squared test. We're going to calculate a particular test statistic. In this case, it's called the t-statistic. We're going to determine the degrees of freedom, and then we're going to look up the critical value relative to this t-distribution. And then we're going to compare our test statistic to this critical value. Before we do that, a quick aside, it's kind of fun. It turns out that the origin of the t-distribution that we're going to use here, student's t, actually comes from beer measurements. As you know, you might or may not know, brewers don't just brew beer, they have to actually test it to see if it's good before sending it to the public. So they do quality control. So a worker at a Guinness brewery came up with a method to use small samples of beer to test its quality. His method used a distribution called the t-distribution, which he published anonymously under the pseudonym A Student. So that's where student's t comes from. Okay, so it looks like this. I said before, I kind of waved with my hands, but now I can see it, a picture. You see that the normal distribution is the top picture here, the top solid line. If you had an infinite number of data points, then a student's t, it's exactly the same as a normal. As you get fewer data points, you see the t flattens out in the center and rises in the tails. So you have a larger chance of getting more extreme values in a t than the equivalent normal. And that chance increases as you lower the number of data points. Okay, so to calculate this, first we calculate the t-statistic, which is this. So it's the square root of the absolute value of your correlation coefficient times this ratio. On the top of this ratio are your number of data points you have, minus 2. And the bottom of the ratio is 1 minus your correlation coefficient squared. Once you calculate that, you get a particular value of the t-statistic. Down here, for our example, we plug in the correlation coefficient here, negative 0.936. We plugged in again here. We have 7 data points. We plug it in, and we end up with a t-statistic of 6.15. The degrees of freedom for this are your data points minus 1. So we have 7 data points minus 1. So you have 6 degrees of freedom. So this is our test statistic and our degrees of freedom. We can now find the table in Appendix B of Cal-Student-Witten, or anywhere else you want to look up t-table online. You will find listing of significant critical values for a particular for particular degrees of freedom and levels of significance. As before, we find the 0.5 line, that's for 95% significance, 95% confidence. We read down to the row for 6 degrees of freedom. We see the critical value is 1.943. Because our test statistic of 6.15 exceeds that, we can reject the null at a 95% confidence level. Actually, in this case, we can reject it at a 99% confidence level. So in this case, we have determined that, in fact, we can reject the null hypothesis that there's no association between our independent and dependent variables. Again, we do not prove our research hypothesis that income and percent employment in government is truly correlated, is truly causally related, but we do reject the null hypothesis that there's no association between per capita income in a state and the percentage of government employees in that state. And that's it. The last one we're going to do in this part of the lecture is the difference of means next. Thank you.